Imagine a world where an unimaginably powerful storm, as big as our planet, is right now raining methane ice. That world is Neptune.
What if everything we thought we knew about Neptune was wrong? New data from cutting-edge telescopes is shaking up our understanding of the most distant planet in our solar system. Magnetic fields behaving unpredictably. Heat where there shouldn't be any. And strange signals coming from deep inside. This isn't just a cold blue world. It might be one of the most complex and mysterious planets we've ever studied. Could Neptune be rewriting the rules of planetary science? For years, Neptune was more of a supporting character in space documentaries and textbooks. It was known as a cold, icy giant, lurking in the outer regions of our solar system, quiet, stable, and largely unchanged since its discovery. But recent developments suggest that this image may be due for a major update.
This is the latest in installments of the astrophysicist's attempt to understand the universe.
The conversation around Neptune shifted dramatically after a public presentation by astrophysicist Neil deGrasse Tyson. Speaking to an audience both in person and online, Tyson brought forward new observations and interpretations that challenge our long-held understanding of the planet. His claims were grounded in data gathered from some of the most advanced space observatories and instruments currently available, including the James Webb Space Telescope and highly sensitive Earth-based interferometric systems. What Tyson revealed sparked widespread curiosity, not just among astronomers, but also among scientists working in planetary physics, chemistry, and even theoretical astrophysics. The reaction wasn't simply because of a few new facts about Neptune. It was because these facts contradicted what many believed to be settled science. It wasn't a minor adjustment. It was the kind of shift that causes people to look again at everything they thought they knew. Before diving into what's changed, it helps to understand where we started. Neptune was discovered in 1846, not by being spotted through a telescope, but by being predicted mathematically. Scientists had noticed that Uranus wasn't moving exactly the way Newton's laws said it should. There seemed to be something else, another object, affecting its orbit. That something turned out to be Neptune. This discovery method alone gave Neptune a mysterious reputation. It wasn't just a faint dot someone stumbled upon. It was a planet that revealed itself through its gravitational fingerprint. Over the next century, astronomers began collecting more data on it, using increasingly powerful telescopes to study its color, orbit, and atmosphere. Then, in 1989, NASA's Voyager 2 spacecraft gave humanity its first, and so far only, close-up look at Neptune. The flyby lasted just a few hours, but it delivered a huge amount of valuable information. We learned about the planet's violent winds, massive storms, and intense cold. Images captured during the flyby showed Neptune as a deep blue sphere, with white methane clouds whipping through its upper atmosphere. The planet also had a giant, dark storm system, not unlike Jupiter's Great Red Spot, although it later disappeared. What Voyager 2 didn't provide, however, was long-term data. We got a snapshot, not a documentary. After that brief encounter, astronomers went back to observing Neptune from afar. Over time, the planet was neatly slotted into our model of the solar system. It was the last of the gas giants, made mostly of hydrogen, helium, and methane, and surrounded by faint rings and a collection of moons. Its place was established, its traits documented, and its mysteries, for the most part, boxed in by assumptions. That is, until now. New observations collected over the past few years have begun to suggest that Neptune is not quite the quiet, stable planet we once thought. With the launch of the James Webb Space Telescope, astronomers have been able to observe planets in our solar system with much greater clarity than ever before. Combined with improved ground-based instruments that can measure magnetic and gravitational fields with high precision, this has opened the door to new possibilities and new questions. Tyson's talk touched on the results of these recent investigations. The images and data revealed patterns in Neptune's orbit and internal activity that don't line up with our current models. For example, parts of Neptune's orbit show small but measurable deviations that don't follow Newton's laws as precisely as expected. This doesn't mean Newton's laws are wrong, but it does suggest there may be forces or internal structures within Neptune that we haven't fully accounted for. Tyson also pointed out inconsistencies in Neptune's gravitational and magnetic fields. These differences hint at a planet that is far more dynamic beneath the surface than previously assumed. Instead of a uniform, layered interior that gets denser towards the center, Neptune might have an internal structure made up of irregular zones. These zones may not follow a simple temperature or pressure gradient, and they could be moving or shifting over time. To the general public, this might sound like a technical detail, but to scientists, it's a huge deal. The structure of a planet's interior affects everything from its magnetic field to its heat emissions to the way it interacts with its moons and surrounding space. The data also indicate that Neptune is releasing more heat than can be explained by solar input alone. At such a distance from the Sun, the planet receives very little sunlight. Yet certain parts of Neptune's atmosphere are warmer than they should be. There's no nearby moon large enough to cause tidal heating, which is one possible explanation for excess warmth on planets like Jupiter. That leaves internal sources, possibly something entirely new or poorly understood. In terms of the magnetic field, scientists have known for years that Neptune's magnetic field is tilted and offset from its center. But the new data shows something stranger. Parts of the field appear to be changing position over time, almost as if they're drifting and reforming. This sort of behavior isn't consistent with how we understand magnetic fields to work on other planets. Most planets generate magnetic fields through a dynamo process, typically involving molten metal or conductive fluids spinning in the core. But Neptune's dynamo may work very differently, possibly involving exotic ices or other high-pressure materials behaving in unfamiliar ways. All of this led to Tyson's central point. Our understanding of Neptune is based on a framework that may no longer apply. That doesn't mean the old models were useless. They were the best interpretations available based on limited data. But now, as our instruments become more precise and as we gather more detailed observations, those models must be re-examined. This is not the first time in science that a long-held belief has been challenged by new evidence. In fact, it's how science progresses, by questioning what we think we know when new information comes to light. What makes this case interesting is the scale of the potential shift. If Neptune operates differently from what we thought, it could mean other planets do too, especially those outside our solar system that we currently classify based on Neptune-like characteristics. One of the main surprises came from analyzing Neptune's gravitational field. Instruments measuring how the planet influences the motion of nearby objects, as well as subtle distortions in background light, revealed inconsistencies in how its mass is distributed. The expectation, based on standard models, is that Neptune would have a relatively predictable structure. A rocky core surrounded by layers of ice and gas, arranged in order of increasing density as you move deeper into the planet. But the data didn't match that picture. Instead, scientists found evidence that Neptune's internal layers may not be neatly stacked at all. There appear to be zones within the planet that are shifting, mixing, and possibly even colliding with one another. This kind of movement suggests a more dynamic internal system than previously assumed, one that is not just layered by gravity or temperature, but influenced by other, still unclear forces. Alongside these gravitational irregularities, the James Webb Telescope detected variations in Neptune's thermal emissions. Some regions beneath the cloud tops were found to be significantly warmer than expected, given the planet's extreme distance from the Sun. At nearly 4.5 billion kilometers away, Neptune receives only a fraction of the sunlight that Earth does. In theory, its atmosphere and surface should be uniformly cold. Yet certain areas appear to generate or retain heat internally, creating warm patches that don't have a clear explanation. This leads to an obvious question: where is the extra heat coming from? One theory is that there could be ongoing processes inside Neptune that generate energy, much like the decay of radioactive materials in Earth's core. However, these processes would need to be unusually powerful or concentrated to have such noticeable effects on a planet this far from the Sun. There's also the possibility that materials within Neptune's interior are undergoing phase changes, transforming from one state of matter to another in ways that release energy. These transitions could involve exotic forms of ice that behave very differently from what we see on Earth. For example, under extremely high pressures, water can enter a state known as superionic ice, where the oxygen atoms form a rigid lattice and the hydrogen ions move freely like a fluid. This creates a substance that is both solid and liquid at the same time, and it can conduct electricity. If Neptune contains large quantities of this material, it might explain both the heat anomalies and some of the planet's other strange behaviors. One of those behaviors is Neptune's magnetic field, which has long puzzled scientists. Unlike Earth's field, which is more or less aligned with the planet's rotation and centered around its core, Neptune's magnetic field is tilted at a sharp angle and significantly offset from the planet's center. What's more, recent data shows that the field isn't stable. It shifts and pulses over time, suggesting that the forces driving it are in constant motion. In most planets, magnetic fields are generated by a dynamo effect, convection currents in a liquid, electrically conductive core that spins and creates magnetic forces. On Earth, this comes from molten iron. On Jupiter, it's thought to come from metallic hydrogen. But Neptune doesn't seem to have either of these in sufficient amounts to explain its magnetic field. Instead, the source may be a shell of conducting ices or other materials that are chemically active under immense pressure. These materials might be circulating in unusual ways, generating a magnetic field that is not only tilted and unstable, but constantly evolving. In fact, some researchers now believe Neptune's interior may contain hollow or partially empty regions, cavities where materials behave like resonant chambers, bouncing electromagnetic and gravitational energy around. These features would be completely unlike anything found in the other gas giants, and they would change how energy and motion travel within the planet. While the idea of a hollow planet might sound like science fiction, in this case it doesn't mean empty space. It means areas with significantly different densities or phases of matter that create complex interactions. There's also evidence of strange radio signals coming from Neptune. The planet has long been known to emit radio waves due to the interaction of its magnetic field with the solar wind, but the new signals don't fit that pattern. They appear to originate from deeper within the planet, and their frequencies don't align with typical atmospheric or magnetospheric activity. While it's still early days, some scientists have suggested that these emissions could point to unusual internal processes, possibly even involving quantum-level behavior of particles under pressure. These are not claims of alien activity or science fiction concepts, but rather observations that challenge our current understanding of how matter behaves under extreme conditions. Neptune is a testing ground for high-pressure physics, and what happens inside the planet might reveal things about materials and energy that can't be reproduced in any lab on Earth. On the atmospheric side, Neptune's extreme weather patterns are also being reconsidered. The planet's winds are the fastest recorded in the solar system, reaching over 1,300 miles per hour. Until now, these winds were thought to be driven by a combination of the planet's rotation and the small amount of solar heat it receives. But with the discovery of heat emerging from within Neptune itself, a new possibility has emerged, that the winds may be powered from the inside out. If that's true, it could mean that Neptune's storms, jet streams, and turbulent patterns are not just reactions to external forces, but symptoms of deep internal processes. These might involve thermal pulses, material phase changes, or shifts in density that ripple through the planet's interior and create massive weather systems. Such a mechanism would be unique among the planets we know and could reshape how we think about atmospheric science in general. All of this makes Neptune an incredibly valuable case study, not just for planetary science, but for exoplanet research as well. Thousands of exoplanets similar in size to Neptune have been discovered in recent years. Often labeled mini-Neptunes or sub-Neptunes, these planets make up one of the most common types of worlds found in other star systems. If our assumptions about Neptune are wrong, then our models of those distant planets may be flawed as well. Understanding what's happening inside Neptune could help us reclassify entire categories of exoplanets, adjust our expectations about their atmospheres, and even reassess which of them might be habitable. This isn't just about one cold, distant planet. It's about the bigger picture of how planets form, evolve, and function across the galaxy. What we are beginning to see is that Neptune may not be the predictable, distant ice giant we once believed it to be. And if Neptune, a planet we've studied for over 175 years, can still surprise us this dramatically, it raises an unsettling but fascinating question. How much else do we think we know that's based on incomplete or inaccurate models? One of the most immediate implications of these findings concerns planetary formation. Neptune is believed to have formed much closer to the Sun before migrating outward to its current position. This process, known as planetary migration, is thought to have played a major role in shaping the structure of the outer solar system. Neptune's gravitational influence is considered a key factor in the development of the Kuiper Belt, a ring of icy objects beyond its orbit. It may have also played a part in the early displacement of other planets, including what some models suggest was a now-lost fifth giant planet. But if Neptune's internal composition and behavior are significantly different from what we expected, it could mean that our models of how it formed and how it moved need to be updated. For example, if Neptune generates more internal heat than previously thought, it might mean the planet held on to more of its original formation energy than expected. That, in turn, could affect its migration path and the gravitational effects it had on surrounding bodies during the solar system's early years. More broadly, the idea that Neptune contains exotic materials, such as superionic ices or plasma-like phases of matter, challenges the assumption that gas giants and ice giants can be neatly categorized. Historically, planets have been grouped into relatively simple types: rocky terrestrial planets, gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. These categories are based on factors like size, composition, and distance from the Sun. But if Neptune contains unusual internal features not seen in other planets, perhaps it no longer fits so easily into the ice giant category. This leads to a more fundamental problem in planetary science: the limits of classification. For a long time, scientists have relied on models that assign planets to specific groups based on a handful of known variables. But those variables, mass, radius, temperature, and orbital distance, might not capture the full complexity of a planet's structure or behavior. If Neptune operates under entirely different physical processes compared to the other giants, we may need to expand or even replace our existing classifications. That issue becomes even more pressing when we consider exoplanets. Thousands of planets have been discovered orbiting stars beyond our own. A large number of these are roughly the same size as Neptune, and many have been classified as mini-Neptunes or sub-Neptunes, based purely on their mass and radius. But if our understanding of Neptune turns out to be flawed or incomplete, it follows that our assumptions about these exoplanets might also be unreliable. This has serious consequences for the study of planetary habitability. When astronomers search for potentially habitable worlds, they often rely on models based on what we know from our own solar system. If a planet is similar in size to Earth, or located in the so-called habitable zone where liquid water could exist, it might be flagged for further investigation. But if even Neptune, a planet we've observed directly, turns out to be more exotic than we imagined, then those same models might be misclassifying or misinterpreting exoplanets based on flawed analogies. There's also the question of whether Neptune represents a transitional or hybrid type of celestial body. While it's far too small to be a star, its unexpected heat generation and unusual electromagnetic behavior could place it in a kind of gray area between planets and failed stars, known as brown dwarfs. Brown dwarfs are objects that are too massive to be considered planets, but not massive enough to sustain nuclear fusion like true stars. They often generate internal heat and have dynamic atmospheres. While Neptune doesn't meet the standard criteria for a brown dwarf, the idea that it could share some characteristics, such as generating unexpected levels of internal energy or having a more complex magnetic structure, might suggest that our categories need to be more flexible. Perhaps planets exist on a broader spectrum than we currently allow, with Neptune occupying a unique spot on that scale. The possibility that Neptune contains hollowed-out or stratified regions, acting as internal resonant chambers, also points toward a deeper need to rethink planetary architecture. If cavities or layered zones inside planets can influence magnetic and gravitational behavior, that could explain previously confusing observations from other celestial bodies as well. It might even apply to moons, exoplanets, or dwarf planets that have shown similarly inconsistent characteristics. Another major implication is how we model planetary weather systems. If Neptune's high-speed winds and massive storms are not being driven primarily by sunlight, but by internal thermal pulses or material phase transitions, then it marks the first time we've identified a planet whose weather might be self-stimulating. This could change how we approach atmospheric science, both in terms of theoretical modeling and in interpreting the data we get from other planetary atmospheres. In practical terms, these findings also highlight the importance of next-generation observational tools. Without the James Webb Space Telescope and recent upgrades to Earth-based observatories, none of these anomalies would have been detected. Tyson was clear in emphasizing this point. Our understanding of the universe is only as good as the tools we use to look at it. As instruments improve, so too does our ability to challenge long-standing assumptions and explore new possibilities. This means the revelations about Neptune are not just a scientific curiosity. They're a reminder of how rapidly our understanding can evolve when new data becomes available. It also underlines the value of sustained investment in space science and technology. The more we're able to observe, the more accurate our models become, and the better we understand not only distant exoplanets, but our own cosmic backyard. The broader lesson here is one of humility. Despite centuries of observation and decades of advanced space exploration, one of our own solar system's planets still has the ability to surprise us. That surprise is not a failure of science, but a success. It's evidence that our models are working within the limits of available information, and that when new data comes in, science is flexible enough to adapt. Tyson's presentation wasn't just a collection of new facts about Neptune. It was a call to reconsider how we think about planetary systems as a whole. It challenged the neat boundaries we've drawn around planets and the assumptions we've made based on limited perspectives. It reminded us that the universe doesn't have to follow our categories. It only has to follow the laws of physics, whether we understand them yet or not. Neptune, once viewed as a cold and quiet planet on the edge of the solar system, now seems to be one of its most dynamic and mysterious members. As we continue to study it, we're likely to uncover even more layers, both literally and metaphorically. And in doing so, we might also gain new insights into the thousands of other planets orbiting stars throughout our galaxy. The story of Neptune is still being written, but already it's forcing us to rethink what it means to be a planet, how solar systems evolve, and how much more there is left to discover.